Good afternoon. So today I will be continuing with the design of fixed portal frame. So as usual, let me brush up what are all the things that I have done in the last class. Let me not go deeper. Okay. So I was doing the design of footing. Okay. So as usual, footing means I want to provide the reinforcement mat. It means that I want the spacing of bars. Okay. If I want the spacing of bars, I want the AST. If I want the AST, I want the bending moment. If I want the bending moment, I want the dimensions. I mean load I want and then the dimension. Okay. I was not knowing the dimension. So that's why what I did, I used the formula sigma minimum is equal to P by A minus M by Z. So using that particular formula, I calculated what should be the length and what should be the breadth. Okay. Then what I did, then I calculated the depth by considering the pressure distribution diagram. Okay. I think till there I have done it. So what was the length that we have provided? It was 2.5 meter, and what was the breadth? It was 1.5 meter, and what was the overall depth? It was 0.34 meter or 340 mm. So I have calculated the dimensions. Okay. So while calculating the depth, so I have calculated the moment also. So now let me take up the area of steel calculation. So as usual, the heading is the portal frame. So under that heading, so I will be going with the first, the next one, that is the area of steel. Under the footing heading, it is the AST. So as I want to calculate the area of steel, I think you people know the formula. Mu is equal to 0.87 Fy AST into D into 1 minus Fy AST divided by FCK B into D. This is the formula. Yes or no? So now what I will be doing is, I know the value of Mu. From the soil pressure distribution, I have calculated M1 and M2, and I have calculated the net moment. So what was that value? So the value that I got there, it was 53.25. Okay, you can check with the previous video. Okay, so it's 53.25 kilonewton meter. I will be converting that into Newton mm is equal to 0.87 Fy AST. Fy I know it, it's 415. AST only I am in need of. Now please be careful. So what will be the effective depth? The overall depth of the footing, it was 340 mm. Out of that, 60 mm effective cover if I deduct it. So what will be the effective cover? So it is, so not effective cover, effective depth. So it is 280 mm. So it is 280 mm. So be careful. Overall depth is 340. Out of that 60 mm cover. So if I remove it, it will be 280 mm into. So 1 minus Fy is 415. AST I need to calculate. Okay. FCK is 20. Please be careful with the breadth as I am calculating the spacing. Okay. So footing I need to go with, assume it as 1000 mm. Okay. So depth, effective depth, it is 280. So be careful with this particular value. So now, what is the value of AST? So the value of AST that we are getting here is 549.08 mm square. 549.08 mm square. As the value of AST is nearer to 400, 500 or something like that, let me go with the AST minimum calculation. So let me cross verify. So whatever the AST that we have provided is sufficient or not. So the next one is check for AST minimum. Okay. I think you people know what is the formula to calculate the AST minimum. So it's 0.12% of breadth 1000 into depth. Overall depth I need to go with. So it's 340 mm. So the final value that we are getting here is 408 mm square. 408 mm square. Okay. Now comparing code suggests that you need to provide a minimum of 408. But what is the AST that we have provided? It's 549.08. So comparing, AST that we have provided is 549.08 mm square. Code suggests AST minimum. It's 408 mm square. So whatever we have provided is more than the minimum value. So hence safe. So I can proceed with this. So now I have calculated the AST. Okay, 549.08. So I want the spacing. If I want the spacing, I need to assume some dia of the bar. So what I will be doing is assuming 12 mm dia bars. I want to calculate the spacing. So assuming, you can even go with 10 mm, no problem. Assuming 12 mm dia bars. Okay, so spacing is equal to pi by 4 into 12 square divided by 549.08 into 1000. So the value that we are getting here is, so it's 205.97. 205.97 mm. Okay. So code suggests one more thing. Spacing is least of the following. Yes or no? Spacing is least of the following. Spacing is least of the following. So the first one is 3 times the effective depth. So 3 times the effective depth is 280. So 0, 24, 2 carry 840 mm I guess. Okay. The next one is 300. So out of this and this. So I can say that 205 is the least. So what I will be doing, let us provide 12 mm dia bars at 200 mm center to center. So provide dia bars at 200 mm center to center. Okay, so we have calculated the spacing. The next thing is, as the footing is resting on the soil, so whenever the load is transferred from the column to the footing and from footing to the surrounding soil, so the footing will be subjected to huge shear with the soil. So that's why I need to do check for shear. Okay, so that I will be going now. So let me rub all these things. So next heading, it is the check for shear. So in check for shear also, especially, so there are 2 types of checks. So one is one-way shear check and the second one is two-way shear check. So first let me go with the one-way shear check. So first one, one-way shear. One-way shear. Okay. So one-way shear is nothing but the normal shear check. That is, the first one is the nominal shear check. So let me go with, and before going with that, I will be explaining one more thing. Observe here. Let me consider this as the footing and let me consider this as the column. So the column is applying the load onto the footing. Observe here what will happen when column applies the load. Don't you think that whenever the column applies the load, so exactly below the column there won't be any shear. If it is there also, it is very minimum. So where the shear will be maximum, observe here, whenever you are applying the load from the column, so this portion are getting uplifted. It means that the shear will be acting at a distance d from the face of the column. So the critical section, okay, starts from at a distance d. So please remember this. So what I will be doing is, in the next line, the critical section for one-way shear is at a distance d from the face of the column. The critical section is at a distance D, distance D. What is this value D? So D is nothing but 280 mm. At a distance D from the face of the column. Okay, so now let me draw a diagram to that. So this is the column portion, this is the footing portion. Okay, let me show the continuation mark here. So I think you people know that this is the total width is 2.5, length I am considering. This is 0.45. Okay, so the critical section will be at a distance D. So I think you people know this is the pressure distribution diagram. I think we know even the values for this. This is 77.72 or 77. It's 72. 72 kilonewton per meter square. On this side it is 3.9 kilonewton per meter square. So at 0 if the stress is like this, okay. So at 2.5 if the stress is 3.9, okay, then what will be the stress at this particular junction? Okay, so that we need to calculate it. So this distance is, so D is equal to 0.28 meter. I know the total distance. So what is this? 1.025. Out of this if I deduct this, so what will be the remaining distance? So the remaining distance is 0.745. Okay, so keeping this in our mind, we'll proceed further. So now what I want is, observe here. So whenever it is 0, it is 77.72. Okay, so whenever it is 2.5, it is 3.9 kilonewton, and whenever it is 0.75, so what is this particular value? Let us calculate it. So we'll go with whenever interpolation using the calculator, whenever it is 0, it is 77.72 kilonewton per meter square. Whenever it is 2.5, it is 3.9 kilonewton per meter square. I want exactly at 0.745 meter. So after doing the interpolation, the value that we are getting here is, so it's 55.72 kilonewton. It's 55.72 kilonewton per meter square. So this value is 55.72 kilonewton per meter square. Okay, so next the same thing. So let me convert this into standard geometrical diagram. So the centroid of this, I will be calling it as W1 and this as W2. So now first we'll calculate the shear force. First we'll calculate the shear force because I want the critical section. Observe here, what is the heading? One-way shear. If I want to calculate that, the first step is nominal shear stress. Yes or no? So nominal shear stress means tau E is equal to Vu by B into D. Vu I don't know. So to calculate that I am doing all these things. Okay. So now I will be calculating the nominal shear stress. So how to calculate that? So there are two forces acting. Okay. So shear force, total shear force is equal to W1 plus W2. So shear force is equal to W1 plus W2. How to calculate this? I think we have already discussed stress is equal to load by area. So load is equal to stress into area. So what is the stress for this? Before that I want to calculate this also. Observe here. So I want this particular distance. So how to calculate this? So 77.72 minus 77.72 minus 55.72. So don't you think that it's 22? Okay, so it's 22 kilonewton per meter square. Okay, I got each and every single value here. So how to calculate this W1? So W1 stress into area. What is the stress for this rectangular portion? So for rectangular portion, the stress is 55.72 kilonewton per meter square. So it's 55.72 kilonewton per meter square into area. So how to calculate the area? So what is this distance? This distance is nothing but 0.745 meter into. So what is the depth it has gone? So we don't know, we'll assume it as 1 meter. So stress into area, one thing over plus one more W2 is there. For W2 it is the triangular portion. So for triangular portion the stress is 22 kilonewton per meter square into area. How to calculate the area of a triangle? So half into base, it is the same thing. So it is 0.745 into, what is the height? I don't know, it's 1 meter. So after solving this, the value that I will be left out with is 49.71 kilonewton. It's 49.71 kilonewton. Okay, so now I want the multiplication factor. It means that I want the maximum value. So VU. Okay, shear force means V. VU I want. So it's 1.5 into 49.71. The value that we are getting here is, so it's 74.57 kilonewton. 74.57 kilonewton. I got the VU value. So now, as the heading itself indicate, let me go with the check for shear. So first one, nominal shear stress. So it's nominal shear stress. It's nominal shear stress tau V. Okay, so tau V is given by VU by B into D. Yes or no? So VU is, just now we have calculated 74.57 into 10 power 3 whole divided by, so breadth is 1000 because it's a footing, depth is 280. So the value that we are getting here is 0.267. It's 0.267 Newton per mm square. Okay, so now what I will be doing is, so let me calculate the next one, that is maximum permissible shear stress. Maximum permissible shear stress, that is tau C max. I think you people know that for M20 grade concrete, table 20, page 73 of IS 456. So what is the value? So tau C max is equal to 2.8 Newton per mm square. So let me compare tau V. So it's 2.267 Newton per mm square, and tau C max, it's 2.8 Newton per mm square. So I can say that tau V is less than tau C, hence safe. So now let me move on with the next one, that is the design shear strength of concrete. So the next heading, let me rub this. I will be keeping this portion as it is. Let me check. Okay, so let me keep it for a while. So let me rub this. So now I will be going with the next one, that is the third one. It is the design shear strength of concrete. That is tau C. If I want to calculate tau C, I need to first go with 100 AST by B into D. Yes or no? So it's 100 into, So the value of AST that we obtained here is 549.08. 549.08 divided by breadth. I will be taking it as 1000, effective depth is 280. So the value that we are getting here, okay, so it's 0.196. It's 0.196. Okay, I want the value of tau c. So where I will be getting that? So from table 19. From table 19, page 73, IS 456. For M20 grade concrete and 100 AST by BD value 0.196, the value I can directly take it by doing the interpolation. So the value is 0.32 Newton per mm square. 0.32 Newton per mm square. Okay, so now observe here. So as it is a footing slab, so I need to go with one more thing. So final tau c value will be like this. Final tau c value will be k times tau c. So what is this value of tau c? I mean, what is the value of that k? So that k value you can obtain, you can get it from page 73 of IS 456. Let me check it out. So it's page 73 of IS 456. Okay, not page 73, it's page 72. So this k value, page 72, you can take it, page 72 of IS 456. Okay, so there is a tabular column given. Okay, so overall depth of the footing slab or the slab, if it is 300 or more, you take it as 1. If it is less than or equal to 150 mm, okay, so they have given certain values. Ours is 340 mm overall depth. So it is 1 we need to consider. Okay, so tau c, so no need to worry. So it's 1 into 0.32. It's 0.32 Newton per mm square. Okay, so now what I will be doing, observe here, comparing tau v, it is 0.267 Newton per mm square. Okay, tau c, 0.32 Newton per mm square. Okay, tau v is not exceeding tau c, tau v is less than tau c, hence safe. Okay, so now I will be doing for two-way shear. Okay, two-way shear. So in both the way I will be checking the shear. This is for one-way shear. So I have checked only in this particular direction, that is 2.5 meter. So now let me be safer and check for two-way shear. So two-way shear means in both the direction. So I will be taking it now. So the next heading, so it's check for two-way shear or check for punching shear. So let me rub all these things. So the next one is check for punching or two-way shear. So this is also one of the important checks, especially for footings. Okay, so now what we will do is, so as in the one-way shear also we have calculated where the critical section lies. Here also we'll do the same thing. So as you people have seen that whenever you apply a load, the footing, so the footing, all the four sides will try to lift at a certain distance. So for one-way shear it was taken as D, but for two-way shear it is taken as D by 2 from the face of the column on all four faces. Observe here. So what I will be doing, the critical section for punching shear, critical section for punching shear will act at a distance of at a distance of D by 2 from face of the column. From face of the column. From face of the column. Okay. So now let me draw a diagram so that you can easily understand that. So this is the footing slab or footing portion. Okay. Instead of writing it as square, let me write it as rectangle. Okay. So this you people know that it's 2.5 meter. This it's 1.5 meter. In the same manner, let me write down the column portion. So I think you people know that this they have given it as 0.45 and this they have given it as 0.3. Okay. So here what I told, so the critical section acts at a distance of D by 2 from face of the column. So D by 2 here also, so D by 2 here also, D by 2 here also, similarly D by 2 here also. Okay. So what we need here is, so from here onwards the critical section takes place. Okay. So the rubbing action, lifting up, so will takes place after this. So it means that this portion we are in need of, please remember. So after this critical section, okay, so the actual shear, the critical shear takes place. I want this particular junction. So let me proceed further now. Okay. So what I will be doing is, first let me calculate, so let me call this distance as L0, let me call this distance as B0. So first let me calculate what is the perimeter of this. What is the perimeter of this? So if I want to calculate perimeter, don't you think that it is the outer entire length of this diagram? So L0 here, if this is L0, obviously this is also L0. If this is B0, obviously this is B0. Okay, so first let me calculate what is this L0 and what is this B0. So L0 is given by D by 2 plus D by 2. Okay, it is nothing but 1 time D plus this width of this, the depth of the column. So it's 0.45 plus D by 2 plus D by 2, that is 1 times D. So finally I can say this is nothing but 1 times D. So it's 0.45 plus 0.28. So the value that I am getting here is 0.73 meter. Similarly, let me go with B0. So B0 value is this distance. So what is this distance? It is nothing but the width of the column 0.3 plus D by 2 plus D by 2. So width of the column plus D by 2 plus D by 2. So which is nothing but equal to D. So finally it's 0.3 plus 0.28. So it's 0.58 meter. So let me calculate the perimeter. So I want the total perimeter of the critical section. Sir, why you are doing all these things? I will be telling this one. So perimeter of critical section. So don't you think that perimeter means outer entire length? So L0 plus B0 plus L0 plus B0. So don't you think that it's 2 times L0 plus B0? So it's 2 times L0 is 0.73, B0 is 0.58. So the final value after solving this is 2.62 meter. It's 2.62 meter. I will be calling this as B dash for time being, the perimeter. Sir, why you have calculated all these things? So now what I want is from code suggestion, from code recommendation, so they have given a formula. So what is that? Observe here. So average upward pressure into area. That is nothing but stress into area. Okay. So I am calculating the load. So I am calculating the load, which is nothing but the shear force load. This load is nothing but the shear force load, which is given by load is equal to stress into area. Yes or no? Stress into area. So what code suggests? So it is nothing but average, okay. So average upward soil pressure, upward soil pressure into. So area means it is the area of critical section. How to calculate the area of critical section? Observe here. So this is the area that I am in need of. How to calculate it? Don't you think that the overall area minus the area of this critical line, if I deduct this entire thing, so don't you think that I will be left out with this particular area? So it is nothing but overall area, as it is rectangle, length into breadth. So it's length into breadth minus of this particular area will give me the remaining area. So it's L naught into B naught. So stress into area. So how to calculate the average upward soil pressure? I think you people know that from pressure distribution diagram. So one extreme end it was 77.77, on the other it was 3.9. So if I take the average, so it's 77.72 plus 3.9 by 2, it's the average, into length is 2.5, breadth is 1.5, L naught is, what is the value? It's 0.73 into B naught is 0.58. So the final value of shear force that we are getting here is, okay, so it is 135.75, 135.75 kilonewton. I want the ultimate value. So VU is equal to 1.5 into 135.75 kilonewton. So after multiplying, the value that we are getting here is 203.63. 203.63 kilonewton. So hardly I will take 5 more minutes. Okay, so first one is nominal shear check. It's nominal shear check, that is tau V. So tau V is given by, as you people know that, it's VU by B into D. So VU value, so be careful, so it's 203.63 into 10 power 3. Be careful, instead of B I am taking it as B dash. Sir, what is the reason? Because that is the area where it is trying to lift up, that is the perimeter of that critical section B dash. So in that particular line, so breadth you need to take it as B dash. What is the value of B dash? It's 2.63, or can I write it like this, 2620 meter. I have converted it into mm into. So what is the effective depth? It's 280. So be careful with this. So the value that we are getting here is, so it's 0.277 Newton per mm square. So tau C max value directly I will be taking. So it is maximum permissible shear stress, maximum permissible shear stress, tau C max, so which is given by 2.8 Newton per mm square from table 20. Table 20, page 73. Okay, so now the third one, I think you people can say that tau V is less than tau C max. Hence, you can say that it is safe. Hence, you can say that it is safe. Hence, safe. So now the last thing. Okay, so now what I will be doing is, I was supposed to take up the design shear strength of concrete, but here what I will be doing is, so instead of design shear strength of concrete, as it is a two-way shear, I will be going with permissible shear stress. Okay, a slight modification in the procedure, it is the permissible shear stress. Okay, so how to do that? So from page 58 of IS 456, from page 58 of IS 4, 5, 6. So permissible shear stress is given by permissible shear stress is given by, so it's K into tau C, but tau C into K. So it's K into tau C. Instead of calling it as K, I will be calling it as Ks into tau C. So what is that value of Ks and what is the value of tau C? So all those things I can easily calculate it. Observe here. If you open page 58 of IS 456, so you have a formula in that. So what is that formula? So where Ks is equal to, where Ks is given by 0.5 plus beta C, and that value should not be greater than or equal to 1. Okay, where one more thing, beta C, where beta C is equal to shorter side of the column divided by the longer side of the column. Shorter side of column divided by longer side of column. So let me do that. Shorter side is 300, longer side is 450. So the beta C value that we are getting here is 0.66. Let me substitute it back. Therefore, Ks is equal to 0.5 plus 0.66. So it is 1.16. It's 1.16. 1 point which is greater than 1. So it should never be greater than 1. So take Ks is equal to 1. Okay. So now let me substitute it back here. So Ks value I got it. How to calculate the tau C value? So we have a formula, tau C is equal to 0.25 times the square root of FCK. So it's 0.25 times square root of 20. So the value that we are getting here is 1.118 Newton per mm square. So the final value, so therefore permissible shear stress is equal to Ks into tau C. Ks is 1, tau C is 1.118. So it's 1.118 only. Okay. So now comparing tau V and permissible shear stress. So tau V is equal to 0.277 Newton per mm square and permissible shear stress is 1.118 Newton per mm square. So which is tau V is less than this, hence safe. So in two-way shear also it is safe. So till here you need to do it. Okay, one-way check and two-way check, both we have done it. So this completes the design of portal frame. Okay, so fixed portal frame, there is one more hinged portal frame. And one more thing, in all the design part I have not drawn the detailing part. I will be doing that also. So for time being we'll wind up. Thank you.